Okay, so think about a pendulum for a second. Like in a big grandfather clock. It's got that steady, calming swing, back and forth, back and forth. Super predictable, right? It's orderly. But what happens if you add just one more moving part to that simple system? Well, that's when things get really interesting.
And this slide just nails the difference. On one side, you've got your standard single-joint pendulum. Simple, rhythmic, you know exactly what it's going to do next. But you add that second joint, and everything changes. It becomes this wild, complex, almost untamable thing. Suddenly, you're not just looking at physics anymore. You've stepped right into the world of mathematical chaos.
So to really get a handle on this chaos, we have to move beyond the stuff we learned in high school physics. That idealized picture of a tiny weight on a perfectly massless string? That's a great place to start, but in the real world, things are a lot more fun.
See, almost every swinging object you'll ever encounter is what's called a physical pendulum. We're not talking about a little point of mass anymore. Think about a baseball bat, or your own leg when you walk, or even just some random piece of wood you find. The mass is spread out all over the object, and that fact completely changes the rules of how it swings.
And the key to understanding that swing is a concept called the moment of inertia. I absolutely love the definition on this slide. Rotational stubbornness. It's perfect. It's just a way of measuring how much an object fights back when you try to spin it. It's why a long, heavy bat is way harder to swing than a short, light one, right? That's its moment of inertia at work. Okay, so let's put these ideas together and get to the main event. It's time to meet the true rock star of complex pendulums, the one that shows off the beautiful, mind-bending rules of chaos better than anything else.
And here it is, the double pendulum. It's so simple in its design, it's literally just one pendulum stuck on the end of another one. But when you let it go, oh man, it whips around, it flips, it makes these gorgeous looping patterns, and it changes direction in a way that looks completely and totally random. This is the poster child for chaos theory.
So as you're watching that incredible, hypnotic motion, you have to wonder, is it really just random? Is there any kind of pattern in there at all? Or is it just noise? And the answer, which is so cool, is a very definite no. It's not random, it's chaotic. And believe me, in the world of physics, random and chaotic are two very, very different things. Randomness means there's no pattern, but chaos has rules.
So how does that work? How can it follow rules but still be unpredictable? Well, it's this amazing paradox. First, the pendulum's movement is 100% determined by the laws of physics. The equations are exact. There's no guesswork. But, and this is the huge but, the system is incredibly sensitive to where it starts. I mean, if you start it from two positions that are almost identical, a difference so small you couldn't even see it, within seconds, their paths will be completely different from each other. That extreme sensitivity is the very heart of chaos. It means that even though it follows the rules perfectly, we can never ever predict what it's going to do.
Now you might be thinking, okay, cool physics toy, but so what? Well, it turns out these ideas aren't just for the lab. The principles of complex pendulums are literally all around us, shaping our world in ways you probably never even thought about.
For instance, just take a walk. Biologists and people who design robots actually model our legs as inverted physical pendulums. Understanding those swinging mechanics is how they build better prosthetic limbs and robots that can walk more naturally. Every single step you take is a little dance with physics.
Or look up. Ever wonder how massive skyscrapers don't just topple over in strong winds? Many of them have a giant device inside called a tuned mass damper. And what is it? It's basically a huge, heavy pendulum near the top of the building. It's designed to swing against the force of the wind, canceling out the sway and keeping the whole structure stable.
And you definitely see it in sports. A gymnast on a high bar is an absolute master of pendulum mechanics. By tucking their body in or stretching it out, they're changing their own momentum of inertia on the fly. That's how they control the speed and height of their swings to pull off those incredible routines. So, let's zoom back out. What's the big takeaway from all this? What does this journey into the wild world of a chaotic pendulum really teach us?
I think the big lesson is this. Incredible complexity can grow from very simple beginnings. All we did was add one extra joint to a predictable system, and it blossomed into something with this infinite, unpredictable beauty. It's a powerful reminder that even the things we think are simple can have amazing depth hidden just beneath the surface. And that really leads to a final, profound idea. When we watch the crazy path of a double pendulum, we're not seeing a system that's broken or has no rules. We're actually seeing a deeper, more complex set of rules playing out. It tells us that physics isn't just about the simple, predictable things. It's about finding the hidden order inside the chaos itself.